Hi everybody, I'm glad to be here with you all again. If you're able to print out the notes packet, that's great, but if you can't, that's no problem. You'll just need some notebook paper or a notebook, and you should be good to go. You don't need to write down every single word on here, just the important definitions, examples, theorems, things like that. I will try to highlight as we go through some of the important ones for you guys to write down. And I will also post the completed notes in Google Classroom, so you'll be able to copy down anything that you're missing later on. Feel free to pause anytime you need to. There's going to be certain times throughout the lesson where I will ask you to pause the tape, and you will be able to do some practice problems on your own. All right, so we are ready to begin. So today we're going to talk about section 10.1, which is arcs and sectors. This entire chapter is about circles. So Darren is wrapping a wire around the circular disc shown below. How long does the wire need to be? So you'll notice that our wire is starting over here, and we need to wrap it around the circle. Okay, now you might recall that there's a word that represents the distance around a circle, and that's called circumference. This is the length around a circle. And we actually have a formula that gives us the circumference, and it's equal to 2 pi times the radius. Sometimes you'll see the circumference written as pi times the diameter. And the reason for that is because 2 times the radius is also a diameter. So either of these formulas work. I tend to use this one. So what we're going to do is determine the radius of the circle, which according to the diagram is 22. So if I were to multiply this out, I would get 44 pi centimeters. Now that doesn't really help us because we need to know how long in centimeters that wire needs to be, and pi kind of throws us off. So we're going to use our calculator and type in 44 pi, and we see that that is 138.23. 138.23 centimeters. So the question says, how long does the wire need to be? Well, it needs to be a total of this length. Now, we've got 100 centimeters over here. My guess is that this piece would have to be 38.23 based on our measurements, okay? So this is the total length of the wire. Okay. Now today we're going to be talking about a lot of new vocabulary words when it comes to circles. And in order for us to discuss these, I actually have a couple circles down below. So we're going to zoom out just a little bit. And we'll be drawing on these circles, marking them up quite a bit as we write in our definitions. Okay, so an arc is going to be a curved, well, actually let's word it as a fractional part of the circle, the curved portion. So if we're looking at this circle over here, I'm going to go ahead and draw in a radius. Okay, we'll call that R. And I'm going to draw another radius. Okay, we don't need to label that one too. And I'm going to put a couple points on this diagram. Let's call this A. Let's call this B. And let's call the circle O. Okay, we always label a circle, give it its name based off of its center. So the symbol that we use, so let's actually put a circle symbol and the letter O. So I would call this whole circle, circle O. Okay, now the arc is going to be the curved portion, and I'm just gonna highlight this slightly in pencil. This portion is called an arc. Okay, and you can kind of picture that as a curved arc. Now the terminology that we use, or the way that we label it, notation-wise, is with the letters that create that arc. And you'll notice the symbol that I put above it is this arced curve, okay? Sometimes we see this word intercepted. We'll talk about that shortly. I'm actually gonna jump toward the central angle. So a central angle, if we're looking at this diagram, would be an angle with its vertex at the center of the circle. So vertex at the center of the circle. Okay, so I would call this angle AOB. And with circles, we generally want to use all three letters there. Okay, now a minor arc has a measure less than 180 degrees. Okay, so if we look at this diagram here, I'm actually going to scoot down a bit. If I were to extend this, you'll notice that, we'll call this C. You'll notice that this is half of a circle because of the diameter, okay? So because of that, my arc up top is definitely less than 180 degrees, okay? So when we have a minor arc, for example, AB, or BC would also be a minor arc because it's definitely less than 180. Okay. So you can probably guess that a major arc is going to have a measure greater than 180. So let's put another point on the circle. I'm going to call this D. Okay. And I don't even need to connect it really. If I were to highlight the arc that goes all the way around, starting at A and ending at D, this would be considered a major arc, okay? So with major arcs, you always want three letters to name. So in this case, I could call it A, B, D. And you still have the arc symbol right above it. Now, could we have called this A, C, D? Absolutely, that would work too, okay? Now, a semicircle has a measure equal to 180. So if we know that half of the circle is going to be 180, we're going to call it ABC. We still use three letters for a semicircle. Okay, arc measure, notice we've talked about it quite a bit. The arc measure is always in degrees. Okay, and it matches the measure of the central angle. So for example, if I know that this angle here is 70 degrees, then the measure of the arc is also going to be 70 degrees. Okay, so we know that a full circle is 360, half a circle would be 180. So if I know that this one's 70, by subtraction, my other angle has to be 110. Okay. Now, congruent arcs have the same measure. Same measure. Okay. Now, if we were, we'll add something to that in a moment. So if we look at this next diagram, we call these concentric circles. Kind of like a target. Okay. Means that they have the same center. So if I were to draw an angle, something like this. And if I were to tell you that this is a 70-degree central angle, well then this arc has to be 70 degrees, and this arc has to be 70 degrees, okay, even though one of the circles is bigger. Now, what's important about congruent arcs is that even though they have the same measure, they also have to have the same radius. And circles with equal radii. So if you're looking at this arc up top compared to this arc over here, the arcs are not congruent because we can clearly see that one of the radii is larger than the other, okay? So these are not congruent arcs, okay? So this last word that I had skipped over is that word intercepted. We use that with arcs a lot. Intercepted means an angle, an arc that's caught by an angle. By the sides of an angle. So for example, if we were looking at this one right here, we would say that arc AB is intercepted, it's intercepted, caught by the sides of this angle. Okay, picture it as like if you were to extend these sides, the arc is in between them. Okay, it's just one of those words that comes up and I wanted to explain it. All right, so let's jump to the next page. And we're gonna use circle W to answer the following. So if we want the measure of arc XZ, so because the central angle matches the arc, we know that it has to be 115 degrees, okay? Now next we're asked to name the major arc. Remember, major means greater than 180. So it can't be this one. It would have to be the one that goes around this way. Now we always want to start with one of the endpoints, go around, and end with the other endpoint. And because it's a major arc, we need 3 letters. So we're going to call this X, Y, Z. Okay, now in terms of finding the measure of the major arc, the whole circle is 360. So in order to find the measure of this new arc, we would take 360 and subtract 115, and that gives us 245 degrees. Okay. And so that's one of the ways that we can find angle measures. Now our next task is to determine how long, what's the actual length of that arc. Now we're going to relate that to the circumference of the circle. So for example, if I'm looking for the length of this arc, we're calling it S, okay? We know that it's a fractional part of the circumference, which is 2 pi r. Now, in order for us to figure out how much of that circumference, we use the central angle. So the central angle which is a degree measure. Central angle, or even the angle measure of the arc, that would be fine as well, over 360, because that's the full circle. And we're going to multiply by 2 pi r. So for example, if I have a circle with a radius of 4, we want the length. Length means how long is it? Okay. And let's call this in inches. 4 inches is our radius. We would take the 80 degrees out of 360. That's how much of the circle we're using, times the total length around the whole circle, which is the circumference. Okay. Now, if I were to put this into my calculator, let's do 80 over 360. You'll notice I'm putting it in parentheses because now I'm going to multiply, well, this is 8 pi, multiply by 8 pi. Okay, I just did the multiplication of this portion in my head. And you'll notice we get 5.59 inches. Now, if we were to draw what that means, let's actually draw a little mini picture here. Okay, we've got our circle. I've got an 80-degree arc, radius of 4, okay? That means the length of this portion, how long is it? If I were to take a string and put it up against that circle, that string would have to be 5.59 inches, okay? Now, degrees is just one of the units of measure that we use, and it's actually the only unit of measure that you guys have ever learned. So today we're going to learn about something called a radian. It's just a different unit of measure. Just like how linear length has inches or centimeters or feet, okay? Those are all different types of units. A radian is another type of measure for angles, okay? So a radian is equal to the measure of a central angle that intercepts an arc with length equal to the radius of the circle. Now that is the wordiest explanation I've ever heard. The best way for us to visualize this is to draw it on a circle. I'm going to draw the radius. Okay, so we've got R. For me to draw a radian is if I were to take this exact same length, let's say it was a string, and I would lay that same string on top of this circle. So I would lay it down and it would hit maybe somewhere over here. Obviously it's curved over on this side, but it's like if we were to straighten it out, it should equal the radius. So it'd be something like that, okay? So this tells me that this would be 1 radian in length, okay? Now, one of the things about a circle is that a whole circle, yeah, we know that it's 360 degrees. Well, how about in radian measure? If I were to go around this whole circle, how many radians would that be? And it actually is 2 pi radians for that whole circle. That's the length around the whole circle, okay? So if we're trying to find the length of an arc using radian measure, we take the central angle in radians and we just multiply it by the radius. It's a lot shorter formula. So we've got the formula right up here. The arc length is equal to, this symbol is just theta. I think we've seen it before, but I'll just reiterate. It's used as a variable for angles. It's kind of like x or y or any other variable. So we're going to say that the arc length is equal to the angle times the radius. Okay, so it's kind of a shorter formula when we're dealing in radians. Now let's do an example problem together. So in a circle with a radius of 6, what is the length of an arc that has a measure of pi radians? So if I write my formula down, my radian measure is right here, so that's pi. Okay, my radius is 6. So that means the length of the arc is going to be 6 pi units. Okay, even if this were a radius of 6 inches, let's say, that means my arc length is 6 pi inches. Now, it's probably more useful for us to put 6 pi and have a decimal equivalent. So we've got 18.85. inches. So in this particular circle, if my radius is 6 inches, the arc is going to be 18.85 inches. Okay, if we're talking about that angled measure. Okay. All right, so now we've got a couple more examples here. I'm going to give you guys a few minutes. I'd like you to pause the video and attempt problems 4 and 5. Okay, so after you work through the problems, give it a try. You can unpause and I will put the worked out solutions right here. Okay, so I have most of the work here for both of these problems. I wrote the initial formula right up top. Okay, so we first needed to find the angle measure for arc AD. So we found that that was 140 degrees. Put that over 360 times 2 pi r. Now, one of the things I want to point out is that the directions say to express the answer in terms of pi. That means I want pi in the final answer. That means this is an exact solution. Exact meaning we're not rounding anything. We're leaving it as exact as possible. Now, I want to show you a little trick in the calculator. Otherwise, it can be kind of tricky to do this. So what I like to do is put the fraction in first in parentheses. Okay. Now, instead of multiplying by 2 pi r, I'm just going to multiply by 8. Okay. And the reason I'm doing this is I don't want to type pi into my calculator because it'll throw things off too much. Okay. So really what that means is I've got 3.111 repeating times pi because I still need to include pi. Now, I want to switch that to a fraction. So I'm going to hit the math button, and number 1 is fraction. So we're converting this to a fraction, which is 28 over 9. So my final answer is going to be 28 over 9 times pi. Okay, because remember we hadn't done anything with the pi in the previous step, so I need to bring it along, okay? So another way that you can write this is 28 pi over 9. It's okay to put it on top. Usually I'll write it like this. Okay, so that is the length of arc AD. Now we're gonna do something similar with this next one. So because we're dealing in radian measure, my formula is a little simple. It's just the angle times the radius. So I have 3 pi over 4 times my radius. I'm going to type this into the calculator. 3/4 times 5. Math, frac, and I get a fraction. 15 over 4 pi. There we go. And we're ready to move on. Okay. Okay, so now we're going to talk about sectors and segments. So a sector of a circle is the region bounded by two radii and its intercepted arc. So that intercepted is coming up again. So what we're talking about here is if I were to highlight one radius and another radius, and the intercepted arc is the arc connecting those endpoints. So you'll notice it's a little bit shaded in. I'm actually going to shade it a little more. This whole section is called a sector. It's kind of like a slice of pizza. So the area of this sector, it's kind of like a part of the whole circle's area. It's a fractional part of the area of the whole circle. So our formula is kind of similar to how we did arc length, where we do the central angle over 360 times pi r squared. Now you'll remember that the area of a circle is pi r squared. So if we're looking for the area of this sector, I would do 78 degrees over 360 times pi r, which is 10, squared. Now, it doesn't say that we need our answer in terms of pi, so I'm just going to type this whole thing into my calculator. Let's clear out some of this stuff. We've got parentheses, 78 over 360. I always like to put that in parentheses. Times pi times 10 squared, pi r squared. And we end up with 68.07. And our unit, because we're talking about area, is going to be centimeters squared. And that would be the area of the sector. Now, if we flip to the next page, I'm going to pause the video and you guys will try to find the area of the shaded sector AFB. Didn't shade very well, so I'm just darkening it for you. So we're looking for the area of this portion. Please pause the video and give that problem a try. All right, so you'll notice that we use the same formula, central angle over 360 times pi r squared, and we get 12.96 units squared. They didn't give us a unit here, so we're just calling it units squared. Now our last little section is talking about a segment of a circle. Now the previous problem was kind of like looking at a slice of pizza, so if we're using that same analogy, it's kind of like the crust. So it's the part of the circle bounded by an arc and the segment joining its endpoints. So if we're looking at this picture, so we've got our pizza slice, the arc is connecting these two, and the chord, that segment connecting these 2 points, is that segment XY. So we're looking at the space in between that straight line and the arc, okay? So in order for us to find the area of this portion, we start by finding the area of the whole slice of pizza, and then we take away the area of this triangle, okay? So if I'm looking for the area of the sector, so the area of the sector, it's equal to, well, we've got 60 over 360 times pi r squared. Now, if I were to throw that into my calculator, I get 33.51 centimeters squared. Now so check, we've got this. Now the other part of this is finding the area of the triangle. Now I'm going to redraw the triangle here. So I've got 60 degrees. And this side is 8, this side is 8, which means that these two angles have to be the same as well. Now, if I were to subtract, we know all three angles have to add up to 360. All three angles in a triangle add up to 180. So if I subtract the 60 degrees, and these are both the same. So if I divide by 2, you'll notice we have another couple 60-degree angles. Okay, so that means we have an equilateral triangle. Okay, now remember that the formula for the area of a triangle is 1/2 base times height. Now I know that the base is 8. Now for us to figure out the height, there's the base, we need the height of the triangle. I'm actually going to mark this a little bit differently. Let's erase this one, just so I can draw down the middle. That is the height that I'm looking for. Now I just divided a 60-degree angle into 2 equal parts. And I hope you notice we now have a 30, 60, 90 triangle on each side. Okay, so instead of calling this piece 8, I can say, okay, this is 4, and this is 4. That would mean that my height, that height is 4√3. Going back to our rules of a 30, 60, 90 triangle. So I know that if I were to plug in my height here, I have 4√3. So this was a little bit trickier just because we did have to bring in our knowledge of 30, 60, 90 triangles. Now I'm going to type this all into my calculator. And we end up with 27.71 centimeters squared. So we found the area of the triangle. Now for the area of the segment, we're just going to subtract, we'll say minus, those two values. So I've got 33.51 minus 27.71, and we get a final answer of 5.8 centimeters squared. And that is our area of, we'll call it kind of like the crust. Now we've got another problem here for you guys to try. Remember, you're using the area of the triangle and the area of the sector, okay? So I'm going to pause the video and you guys can try this next problem. Okay, so we just plugged our values in. The area of the sector, angle over 360 times pi r squared, minus 1/2 base times height. Lucky for this one, our base and our height are both 10 because they make a right angle, so not as much work to do here. And once I plug this into my calculator, the area of the segment is 28.54 feet squared. And we're good to go. All right, let's flip to our very last page. Okay, these last few problems are practice problems for you guys to try. I will put the worked out solutions as part of the scan notes that I put in, so you guys can just give these a try on your own. If you need to go back to any of the problems that I went over, you're welcome to look back at the videos, or you can just look at the worked out notes that are posted in Google Classroom. If you have questions, please contact me during my office hours anytime this week. And I hope you guys enjoyed this. Talk to you soon. Bye-bye.